So we've been talking about different tests to decide if a series converges or diverges. And today we're going to look at the comparison test after we do this last slide from the previous section. And this is just sort of an interesting question. We can imagine stacking dominoes or bricks. And the question is, can we stack them in a way that the top domino will be completely clear of the original base domino without it toppling over? So that's the question in our mind right now. Can we imagine stacking these dominoes in a way that we can get the top one clear of the base without it falling over? What do you think? Can we do that? Probably. Probably? Yeah. And the answer is yes. So then the next question becomes, what's the minimal number that we need? And is there a maximum number? Is there a maximum distance that we can get in terms of clearance? And so here is the setup. So the idea would be, if we want to create the maximum overhang, we're going to put the left edge of the top domino right on the center of mass of the lower domino. And if we do that, if our parts are machined perfectly so that there is crisp edges, if you place those two dominoes, this is the maximum overhang that you could have and it not topple over if you have that left edge right at the center of mass of the lower one. Okay, so that total overhang, I'm going to consider each domino 2 units long, so the overhang here would be 1 unit. Well, then the next thing that we're going to do is take those 2 dominoes and place them in a way that the center of mass is lined up again. And so we're going to place those 2 in a way that the center of mass of those 2 is right at the right edge here. So the same thing we did here. We took the center of mass of the top one and placed it at the right edge. Now we're going to take the center of mass of the stack of 2, and that center of mass of the stack of 2 is right there, and we're going to place that at the right edge. Well, that creates an overhang now of 1 plus a half, and then we're going to take that group of 3 and take their center of mass. Their center of mass is going to be right here. That's the center of mass for the 3, and we're going to place that at the edge of the next one. And if we keep on doing that, notice the sequence that we get. The overhang is 1 plus a half plus a third plus a fourth. What series is that?
Harmonic.
The harmonic, and it diverges. So this tells us that we can actually create overhang as far as we want if we have perfectly machined bricks or dominoes or whatever, blocks. You can do it pretty easily with bricks and dominoes. You can't quite do it with this. So let's see, our original domino is going to be hanging over when we get to 5. Most people can't do it with 5, but with 6 or 7, you can make it work with our unrefined dominoes or bricks. But you can get it to hang over at least. So that's the first question. And the second question is, you can actually get it to go as far as you want. You can create a huge, crazy wave and not have it collapse, which is kind of interesting. Not obvious to most of us initially when we see the problem. Okay, so that is the end of 10.4. The big thing in 10.4, the integral test and p-series. And now we're going to go into 10.5, which is where we're going to do the so-called comparison tests. And the comparison tests are going to help us, especially when we have things that look almost like a p-series but aren't quite a p-series. So let's first get the logic down. So we're going to assume that we've got a pair of series, and we're dealing with just positive terms for now. So we have an infinite sum of a's, an infinite sum of b's, and all the numbers are positive. So you're just imagining these 2 different series. If we have our series satisfy this condition, that the B's are bigger than the A's systematically, so all the way through. So this says that B1 is bigger than A1, bigger than or equal to. So all the way through, the B's are bigger than the A's. That's how I'm thinking of that. The B's are bigger than the A's. So if the B's are bigger than the A's, and the B's converge, and all the numbers are positive, so there's no weird wobbling around. Everything's positive, so as you add another term, the sums are getting bigger and bigger and bigger. If the B's converge, don't the A's have to converge? Right? If the A's are smaller than the B's, and you add up all the B's, and that converges, well, if you add up all the A's, they're smaller, they have to converge also. So that's our basic logic. Our basic logic is smaller than converging must also converge. Smaller than converging must also converge. So if you add up all the B's, and they converge, and the A's are smaller, and you add all them up, that's got to converge also. There's no escape. They have to converge. So that's our first one. Our second one says, okay, let's suppose the B's are smaller than the A's. So the B's are smaller than the A's, and the B's diverge. So if we add up all the B's are diverging, and the B's are smaller than the A's, so if we add up all the A's, that must also diverge. So this top one, smaller than converging converges. The second one, greater than diverging diverges. All right, so that's our intuition that we want to get rock solid on. Smaller than converging converges, bigger than diverging diverges. And if you're bigger than converging, who knows? Right? If the smaller one converges, that doesn't tell us anything about the bigger one. Right? And so when we're looking at this, so we're analyzing. Here we're trying to make a conclusion about the A series. In both of these, the series we're analyzing has the A's. We're trying to decide, does it converge or diverge? So I think of the A's as we go through this. I think of the A as, in my mind, to give me a cue, I think of A for analyze. So that's the series we're trying to investigate. We're trying to figure out, does the series of A's converge or diverge? The B series is going to be the series that we're going to compare to. The B series is sort of our known series. It's a series that we know it diverges or we know it converges. And we're going to take our A series and compare it to the B series. So if we start with a B series that converges and our A series is smaller than it, then it must also converge. If we start with a B series that diverges and our A's are bigger than the B's, then the A's must also diverge. So the A's we're analyzing, the B's are our comparison series. Okay. And so again, here's this comment that when we're looking at a series, for a series to converge, we're curious about the tail of the series. It doesn't matter what happens in the first finite number of terms. It's out at the tail that dictates whether we have convergence or divergence for a series, just like for a sequence. So here, let's look at an example. So on Tuesday, we talked about P series. And again, let's reiterate that a P series has the form 1 over k to the P. So what is the value of P in that P series? 2. And so we identify that. We say, okay, P is equal to 2. That's how I know you know it's a P series. You've said P is 2. And then we compare this to what number? 1. And that's bigger than 1, so our conclusion is converge or diverge? Converge. So a P series, as long as P is bigger than 1, we have convergence. And here's where one of the easy places to get tangled up kind of is illustrated. With a geometric series, when does a geometric series converge?
Less than 1.
So a geometric series remember that a geometric series has the form, usually we start a geometric series at 0, and this is the most generic form for a geometric series. And a geometric series converges if the magnitude of r is less than 1. So we've got to remember there's a difference here. Here we're going greater than 1. Here we're going less than 1. So there's a little bit of, this is a place you can get confused. It's like, okay, I know I compare to 1, but do I converge if it's less or greater? And so the thing to remember is that with a p-series, you're looking in the denominator. So the power on k has to be bigger than 1. You're in the denominator doing your analysis, versus a geometric series, you're in the numerator. Right? This r is in the numerator. You can think of this all as over 1 if you wanted. Right? So with a geometric series, less than 1 in the numerator, but in the denominator with a p-series, you're greater than 1 for convergence. Okay? So here we're thinking about that repeated multiplication. If you take a number that's less than 1, say a half, and you do repeated multiplication, a half times a half times a half times a half, it's getting smaller and smaller and smaller. So it's less than 1 that goes to 0 fast. Here with the p-series, in order for these fractions to go to 0 fast, the power on k has to be bigger than 1. Right? Because we want the denominator to get bigger so the fractions get smaller. So just keep that idea in mind, that it depends on if you're in the denominator or the numerator. Okay, so that is a p-series, 1 over k to the p. That is a p-series. This one is not a p-series. It's p-series-ish. It's very close to this p-series. And I don't think anyone in here would say, oh, this one might diverge. You know, adding 10 in the denominator is pretty insignificant compared to a squaring of a k when k is 1 million or 2 million or 10 million or 1 billion. So none of us would think that this does anything but converge, but it's not a p-series. So you could use the integral test here and get an arctangent, and you could prove that it converges using an arctangent. But we have these two new tests. One is called the direct, this is usually referred to as the direct comparison test. And then we're going to have a second comparison test called the limit comparison test. So we're going to have two comparison tests. And the direct comparison is what we like to use whenever possible when we have a p-series as our b sub k. So remember up here, the series that we're analyzing is the A series, and the series that's our base series, the series that we know, that's our B series. So right here, this is the B sub k series. This is the one that we know. That's the one we have in the bag. We know that that's a P series. We see that P is 2. It's bigger than 1, so it converges. So this is our comparison series. This is the A sub k series. This is the one we're analyzing. So again, I think of the A meaning analyze, B for base, or whatever you want to do. It's the comparison series. And so our rule was smaller than converging converges. So if we can show, and I'm going to write it this way, I'm going to say WTS, I want to show, if I can show that the A sub k's are less than or equal to the B sub k's, then we'll have convergence. Because the B sub k series converges, and if the series we're analyzing has terms that are systematically smaller, then it must also converge. Smaller than converging converges. So that's what we want to show. So we take our A sub k series that we're analyzing. We don't know if this is true, so I'm going to put a question mark there, and we're going to compare it to the B sub k series. So if we can show that that inequality is true, then we can conclude that the A sub k series converges by comparison to the B sub k series. So here we're going to do cross multiplication. And almost always, you will be able to reduce this down to an inequality that you can solve by inspection. So we get that down there to the end. Obviously, that's true. So if that's true, our conclusion is, therefore, the A sub k series, that's always the one we're analyzing, converges by comparison. So the A sub k series is always the one you're looking at. So we can say that. We don't have to rewrite this whole thing if we don't want. If you just say series A sub k, it's the one you're analyzing. It's the one we are trying to figure out whether it converges or diverges. Okay, so does that logic all make sense? So now let's use the other train of thought. So we just did a smaller than converging will have to converge. Now let's do greater than diverging must diverge. So let's look at this setup here. So this is our B sub k series right here. This is the one we know, right down here. This one, if we rewrite this with a fractional exponent, we have 1 over k to the 1/2. And what is p in this case? 1/2. P is 1/2. So first we make sure it's in this sort of standard form, or, I mean, you could go right from here and say p is 1/2. That's totally fine. This is less than 1, therefore diverge. So for a p series, bigger than 1 converge, less than 1 diverge. Okay, so we have a divergent series. When we look at this series looks really similar to that. This minuscule subtraction by 3 should be insignificant. You imagine massive values of k. K is 1 million, 2 million, 5 million, 1 billion. You subtract 3, that's meaningless. So our suspicion is that, oh yeah, that's got to diverge also, right? There's no way that subtraction of 3 is all of a sudden going to make the series converge. All right, so our comparison series, one question that you're going to ask yourself is, how do you create this comparison series? How do you create this comparison series? So these are our comparison series, our base series, our series that we know, we have them in the bag. Well, we create them by taking away the insignificant pieces of the series you're analyzing. So you construct the B series by pulling off anything that seems insignificant. So chopping off that 10 gives us our base series here. Chopping off this subtraction of 3 would give us our base series here. So that's how we create our B series. So now our want to show is going to look a little different. So here we want to show that the A's are bigger than the B's. Because we have a divergent B series, if we can show the A's are bigger, we know that our logic is bigger than diverging diverges. So we jump in and we say, okay, well, our A series, that's the series we're analyzing. We've got this as our A sub k. We don't know if this inequality holds yet or not, so we put a question mark. And we've got that. So that's the inequality we want to verify. If we can show that that inequality is true, then we know we have divergence. So once again, we're going to do our cross multiplication. Cross multiplication, multiply both sides by the common denominator. We square both sides. And 95 or more percent of the time, you can get all the way down to some numerical inequality that you can solve by inspection. So we get all the way down to that. Is that true or false? That's true. So if that's true, then the series we're analyzing, the A sub k series, A sub k always represents the series we're analyzing. diverges by comparison. So pretty logical, the comparison test. Let's try a couple more. Okay, so the comparison test works when you can show smaller than converging. So we look at this p-series. This p-series converges because p is 2 and it's bigger than 1. Do we think the comparison test is going to work here? So one of the pieces of logic is that, well, if we add 1 in the denominator, we've increased the denominator from this one. So if you increase the denominator, doesn't that shrink the fraction value? Right? So the fraction value here is going to be less than the fraction value here because this denominator is bigger. All right. So that's a clue that the comparison test is going to work here. And we're going to see that sometimes, we're going to see very soon, well, actually, right here. So what about here? Would the regular comparison test work here? Well, here we've shrunk the denominator. We've subtracted 1. So that increases the fraction. So this a sub k will not be less than this b sub k. So the comparison test is not going to work for this one. Okay, so for this one, though, no problem. For this one, so we have that this series up here converges. So our want to show here, we're going to want to show that our a sub k's are smaller than the b sub k's. So b sub k's is always, the series that we're using as our base series, our comparison series. So here we would want to show this, which would mean that we would want to show there the a sub k's. We want to know, are they smaller than the b sub k's? And intuitively, yeah, we've already worked it out. We know it's going to work because bigger denominator, smaller fraction. We've already worked it out, but we've got to do the math. And so we end up with an inequality that we can solve by inspection. That's true. So that tells us that we have convergence by comparison. Now, when we're mindlessly creating our b sub k series, we just ditch anything that's insignificant. So for both of these, the natural series to compare to is 1 over k squared. And if we don't think about the intuition of, ooh, this denominator is smaller, so that means this fraction's bigger, we can mindlessly go through this and we'll end up with the following. We still would like to show the only way the comparison test is going to work here is if those a's are smaller than the b's that converge. And so let's just play this out. We know it's not going to work, but let's play it out. So when we do our cross multiplication, we're ending up with this. And when we subtract off the k squareds, we get that. This is false. And if that's false, that tells us that this test is inconclusive. And so anytime we have something that's inconclusive, we have to go to another test. So like the divergence test is a classic one. The divergence test, like if we look at the divergence test here, we would take the limit of a sub k, and the limit of this a sub k is 0, and that's inconclusive. If a sub k's limit is 0, that tells us the series might converge, still might diverge. So that test becomes inconclusive. Whereas if the limit of a sub k is 2, then we know it diverges. If the limit is not 0, it diverges. So divergence test is often inconclusive, like it would be here. And in this case, the direct comparison test is inconclusive. So the strategy, if we come up to an inconclusive outcome here, is the other comparison test, which we'll get to, called the limit comparison test. But the direct comparison test will not work in that particular case. So what does this limit comparison test do? So we've got, like in the prior example, we know that series has got to converge. We just are not meeting the inequality requirement for the direct comparison test to be the nail in the coffin. And so we go to this limit comparison test. So this says, so the A's and the B's mean the same thing. We're going to take the limit of A sub k over B sub k. So B sub k is our comparison series. A sub k is the one we're analyzing. And if that limit is a positive real, remember that the A's and the B's are all positive, so there's no possibility of a negative here anyway. But if this limit is a positive real, so that's what this statement here means. It's some real number between 0 and infinity, so it's a positive real. So the way that we've been notating that, we could say that L is an element of the positive reals. This means the same exact thing. L is an element of the positive reals. So if that is true, our conclusion is these series do the same thing. They both converge or they both diverge. Both converge or both diverge. Okay, so let's try it. So here's the series we were just looking at a second ago. And just recall that the B sub k series that we're using, so the B sub k series, that is the one where we just ditch the -1. So we're creating this P series. We identify it as P series. We compare it to 1, so we know that this thing converges. So that's our first step. So the B sub k series is 1 over k squared. P is 2 greater than 1, so it converges. All right, but we just showed a moment ago that the direct comparison test was inconclusive. So let's try this limit comparison test thing. So limit comparison test, LCT. So the limit comparison test, we take the limit as k goes to infinity of A sub k divided by B sub k. So that will be the limit of A sub k is 1 over k squared minus 1 divided by B sub k, which is 1 over k squared. So this will be the limit of k squared divided by k squared minus 1. And what is that limit? So we have our 3 ways to get to that limit. We could use L'Hopital's rule twice. We could divide everything by k squared. Or we could use the college algebra argument that you have a quadratic over a quadratic, so you look at the coefficient of leading terms, 1 over 1. So it doesn't matter which technique you use. So if we divided everything by k squared, that's sort of the easiest one to illustrate. And then the 1 over k squareds go to 0, and this limit becomes 1. Okay, so that is a positive real. So we can indicate that in a couple of ways. So this is sort of the quickest and easiest way to just do it, mathematically using that notation. 1 is an element of the positive reals, so therefore we have convergence by the limit comparison test. We get a positive real. So let's try this one again, this test again. So let's suppose we have this series. What is the obvious B sub k series?
1 over k.
1 over k. So the b sub k series we obtain by taking away insignificant pieces of the a sub k series. And of course, that's kind of a loose definition. Take away the insignificant parts. So case by case basis, we have to just make an assessment of what seems insignificant. Adding 1 in the denominator to k, where k is going to infinity, is insignificant. And so we have to say what this series does. We have a couple of ways to say it. And probably the easiest way is mathematically you could say p is equal to 1, and this is not greater than, trying to draw the not greater than symbol. So that is not greater than 1, therefore diverge. So a p series, if p is bigger than 1, we have convergence. So if it's not bigger than 1, we have divergence. So you could say that, or you could say that it's less than or equal to 1. There's a couple of ways you could indicate it. You could also say this. You could also say that this is the harmonic series. So you could also sort of get away from the math symbols and just say the harmonic series diverges. So whatever you want, you can do it symbolically with symbols, or you can do it with a little phrase, the harmonics identify as the harmonic series, and we know it diverges. Regardless, we know we have a divergent b sub k. So the direct comparison test, which is always our first choice when we're dealing with the comparison tests, we would like to use direct comparison if we can. And if we wanted to use direct comparison, we would want to show that the a sub k's are bigger or smaller than the b sub k's. So the b sub k series diverges. So if we can show that the a sub k's are bigger than the b sub k's, then that series must also diverge. So direct comparison would be if we could show this. Now intuitively, let's think. So we've got this series here. This k turns into a k plus 1, so that denominator is increasing. If the denominator is increasing, the fraction is smaller. So we're not going to be able to show this. So let's just go through the math, though, because we want to just verify that we can't use the direct comparison. It's always our first choice when it comes to comparison. So we would want to show that the a's are bigger than the b's because we're trying to show divergence. And we get to this place right here. We subtract the k, and we come up with a false statement. So if that's false, then this test is inconclusive. So that's why we go to the limit comparison test. We always start with the direct comparison. And an obvious question is, well, if the direct comparison test fails and we're going to go to the limit comparison, couldn't we just start with the limit comparison? There are series for which the limit comparison test fails, and you have to go to the direct comparison. So that is pretty infrequent. So most of the time, you could just get away with going to the limit comparison, but we don't do that. It's really important to make sure that you get this logic sort of streamlined in your head. So the test will say show by direct comparison. If the direct comparison doesn't work, then go to limit comparison. Don't just jump to limit. So you want to go through the direct comparison first. This is where most of the logic sits. You know, this whole bigger than diverging diverges, smaller than converging converges. And setting this up and going through it demonstrates that you understand that. Okay, so now we go to limit comparison test. Direct comparison failed, so we go to limit comparison. We're going to take the limit as k goes to infinity of a sub k over b sub k. So this will be the limit of, let's see, a sub k is 1 over k plus 1. It's always the series we're analyzing. B sub k is our base series. It's the one we know. It's the one we created. It's the one we built. B for built. B for base. So we get, once again, to a nice easy limit. That limit is 1. Once again, 3 ways to do it, L'Hopital's rule, whatever. 1, this is an element of the positive reals. So therefore, both series do the same thing. So if your base series converge, they would both converge. If your base series diverges, they both diverge. So therefore, diverge by LCT. So positive real, that means both series do the same thing. So if we fiddle with the direct comparison and we get something inconclusive, then we jump to the limit comparison. All right, any questions on any of the steps with those 2 examples? Pretty intuitive, hopefully, so far. Bigger than converging is meaningless. Smaller than converging converges. Smaller than diverging is meaningless, but bigger than diverging diverges. So some basic logic. Okay, so the question that often arises is, well, how do we build B sub k? So B sub k we build, it's our base series, it's one that we can analyze instantly. We know right away. So when we look at this, I would say to myself, oh, that 3 is insignificant. And if we pop off the 3, I'm going to build the B sub k by taking that away. Now this B sub k, we're not done yet though, because B sub k needs to be something that we can analyze instantaneously. And so we're going to simplify this, and this will end up being k to the 3/2 in the denominator. So we have a k to the 1/2 in the numerator, a k to the 2 in the denominator. So in the denominator, if we pulled that 1/2 down, it would be a negative 1/2, so 2 minus 1/2 is 3/2. Now we have a p series. So the B sub k series has a p equal to 3/2, which is greater than 1, which is convergent. So our suspicion is that this series is going to act the same way that this convergent p series acts. Our suspicion is that that is going to converge by comparison. So let's try. So we would want to show, so if we're trying to show convergence, we put our a sub k's and our b sub k's right there. If we want to show convergence, do we want to put a less than or a greater than in between those two? Less than. Right, since our B sub k series, the one that we built, since that one converges, if we can show that the a's are less than the b's, then the a series must converge also. All right, so that's our logic. And then we're going to just sort of fill in the blanks here, put in the a sub k series, the one we're analyzing, B sub k series, the one we just built. So that's what we want to prove. If we can show that that's true, then we're done. So we cross multiply. So the k to the 3/2 comes up here, and we get k squared, right? K to the 3/2 times k to the 1/2 is k to the 2. And we subtract off the k squareds, and we get to a numerical inequality that we can solve by inspection. We know that that's true. So that's true, which tells us the a sub k series, that's the one, if we want to refer to it, a sub k series is always the one we're analyzing. It's the one that we're trying to test. Converge or diverge? Converge. Yeah, that's going to converge. And here I'll just say by direct comparison test, since We didn't say it anywhere else, so that's by direct comparison test. All right, so you all try this one. So build your B sub k, figure out your WTS statement, what you want to show, and see if you can conclude that it, what do you think? Would it converge or diverge with an exponential growth in the denominator?
It's going to converge.
Exponential in the denominator means the denominator is growing wicked fast, so the fractions are going to zero wicked fast. So convergence, yes. So let's see if you can do it by direct comparison, and if not, jump to limit comparison. What type of series is the 1 over b to the k? How do you confirm that it converges? We intuitively know it converges because the denominator is growing so fast. What type of series is that? Is it a p-series? Definitely not, because p-series is always 1 over k to the p. So with the p-series, the k is in the base of that exponential expression. What is that series? We did spend a lot of time doing this type of series earlier.
It's not geometric.
It is.
Oh.
It is. So to show that it's geometric, we would write it like this. All right? That is what it... Mm-hmm. So what is the r value? R is 1/5, so this is how I know you know it's geometric, because you've identified r. This is less than 1, which tells you convergence. So a G series, geometric series, less than 1 is converging for geometric. So that's how you prove that little piece of it. So do we want to show the A's are bigger or smaller than the B's? Smaller, because the B's that we built, we showed that that's a convergent geometric series. So if we can show the A's are smaller than the B's, then the A series has to converge also. Exactly. So we wanted it to look like that. Let me just fill in the blanks. Cross multiply. Subtract the 5 to the k's. We have a true statement there. So if that's a true statement, then we have that the series we're analyzing, the A sub k series, converges. And we were able to use direct comparison test. So if we change this a little bit, notice this. If we went and made this 5 to the k minus 3, would direct comparison work there? Direct comparison won't work because we shrunk the denominator, which means we increased the fraction. So the a's would be bigger than the b's instead of less than. So here, we would still sort of blindly say, oh, well, let's try direct comparison, and let's just show that it's not going to work. So we're going to have our 1 over 5 to the k plus 3. We would love it to be less than this, and I need that to be a minus in there. But of course, this is going to fail. So this is going to, we're going to make the conclusion that this is inconclusive. So we get that 0 is less than negative 3. That is false, therefore inconclusive. So what would we go to then? Limit comparison. So you guys try the limit comparison test now. So do the LCT with this one. All kinds.
So here, that is true that you could use L'Hopital's rule, but if you use L'Hopital's rule, you would have to take the derivative of each of these. And the derivative of an exponential is itself times the natural log of the base. So it's going to be easier at this stage if you just divide everything by 5 to the k. So if you make that, then you can conclude definitively.
Yeah, this is an interesting one because you do get to, well, let me run through it. So we're going to have limit of A over B. So we'll end up with the limit of 5 to the k over 5 to the k minus 3. So this isn't a polynomial over a polynomial, so we can't look at leading coefficients or anything like that. This is an indeterminate form of infinity over infinity, so you could use L'Hopital's rule. That's a possibility. And if we did use L'Hopital's rule, let's do it 2 different ways here, just so I can show you both. So if we did use L'Hopital's rule, if we had infinity over infinity, we would have to take the derivative of top and bottom, and the derivative of an exponential is itself times the natural log of the base. And in the denominator, we're going to end up with the same thing because the derivative of 3 is 0. And so what would this limit end up being? 1, right? Because they have the exact same numerator and denominator. Or you could do this. which will be a little bit simpler, if you divide everything through by 5 to the k, so you take sort of the dominant term and divide everything by that dominant term. If you divide everything by this dominant term, what's true about this 3 over 5 to the k? Where does that go?
Zero.
Yeah, that's going to go to 0. That little fraction will go to 0, so we'll have 1 divided by 1 minus 0, which is going to be 1. So in either case, we are going to get 1, which is a positive real. And our conclusion, if we get a positive real, is that both series do the same thing. And since our comparison series converged, we're going to get that both converge. So we're going to have converge using that limit comparison test. That makes sense? So limit comparison, if the direct comparison is inconclusive, evaluate limits using L'Hopital or divide by the dominant term. Okay, so now here there is, when we're building the B sub k, we are ditching the insignificant pieces of the summand of the A sub k. So there's our A sub k. And everything is relative. So, like for example, if we had a factorial function and an exponential function being subtracted, the factorial function grows so much faster than an exponential that the exponential, which normally seems pretty significant, is all of a sudden insignificant. So there's this relative nature to picking what's insignificant. Here, both of these are exponentials, but a 3 to the k is going to grow faster than a 2 to the k. So in my mind, what I'm thinking of is that comparatively speaking, 3 to the k dominates 2 to the k, so I'm just going to ditch the 2 to the k. And I'm going to try, and if you try a B sub k and you get nowhere, no harm, no foul. Just try again. Try a different B sub k. So what type of series is this B sub k? Geometric, exactly. And we write it in this geometric form. It's a little more obvious that it's geometric. Then we have the r to the k look, and we would identify r, we compare it to 1, and we make our conclusion. If r is less than 1, we have convergence. So now our base or comparison series converges. So we assume that the A sub k series probably converges. So if we want to show that the A sub k series converges, we would want to show that A sub k is less than the B sub k. So if the series that we're analyzing has smaller terms, then it must also converge. So let's see. So this is what we would want to show. We don't know if that's true or not, so I'm going to put the question mark, and that's going to be B sub k on the right. Now, think for a moment before we do the math. Are we going to be able to show that? Is that going to be true? Well, if you have this denominator here, this denominator is smaller because you do some subtraction. So these fractions are bigger. Right? If we've got this denominator and we subtract some stuff off, this denominator's got to be smaller, which means this fraction is going to be bigger. So we're not going to be able to show this is true. So we get down to here. We have that. So 2 to the k is positive, and if you multiply by a negative, that right-hand side is always negative. Negative is not greater than 0, so this is false. So this means that the direct comparison is inconclusive. Okay, so let's go to the limit comparison then. So limit comparison, let's see, squeeze it in right here. We're going to take the limit of a sub k divided by b sub k as k goes to infinity. So this will be the limit of a sub k, the original, and if we're going to divide by b sub k, that's the same as multiplying by the reciprocal of b sub k. So we do that. Let's, I guess, go this way. And then I'm going to divide by the dominant term. I'm going to divide by 3 to the k, top and bottom. And we get that. So divide 3 to the k by 3 to the k and get 1. Divide 3 to the k by 3 to the k and get 1. Divide 2 to the k by 3 to the k, and then peel out that exponent so we have 2/3 to the k. And what does 2/3 to the k do as k goes to infinity?
Go to 0.
Everybody see that? So if you take a number that's a proper fraction, number less than 1, and you do repeated multiplication by itself, it goes to 0. 2/3 times 2/3 is 4/9, which is less than 2/3. So what's the overall limit here then? 1, which is an element of the positive reals. Oh my gosh. I thought it froze for a second. I didn't draw the stroke and I panicked. All right, so therefore we have what? Convergence or divergence?
Convergence.
Convergence, because our comparison series converged. Yeah. Yeah. You got it. You got it. Okay. Let's see. Yeah, let's do one more and then we'll take a break. All right. Let's take a peek at this denominator. We have these two terms here. Which one goes to infinity faster? 2k or square root of k?
Square root of k.
False.
No, 2k. Oh, 2k.
Right? Square root of k is a bird wing.
Right.
It's going to look like that. It's going to be an arc. And so that's going to go to infinity at a certain pace, but an identity function like y equals x or y equals k, and 2k is even steeper. So that k is going to dominate. So when we build our b sub k, in this particular case, we are thinking of that root k as insignificant. So we are thinking about this series. Now, you could also make the argument that that 2 is pretty insignificant, because right now it's not a harmonic, but it's harmonic-like, for sure. So we could choose, you could just leave that, or you could try to go even smaller, or sort of more, pare it back even further and say, hey, let's get rid of the 2. Let's go with this one first. Let's go with this and just see what happens. So let's try this one and see what happens. This one is harmonic, correct? So it diverges. So you could make a p-series argument that p is equal to 1 and that's not less than, or it's not greater than 1, so therefore it diverges. Or you can just say it's harmonic, therefore it diverges. So we suspect that this one up here diverges. Now, will we be able to show that? Let's find out. So we would want to show that the a sub k's are bigger than the b sub k's, because bigger than diverging diverges. Can we show that? Let's find out. So we're going to plug in the a sub k. We want to show this. This one's going to be a little squirrely. We do our cross multiplication, and we subtract k, subtract 2k. So we get that. Let's go ahead and square both sides. Although we have to be a little bit careful, actually, because let's write down an inequality that's true over here. -4, that's less than -1, right? And if you square both sides when you still have the negative, is that true? The whole squaring, right, if you have -4 and -1 and you square both sides,
Yep.
that's false, right?
Yep.
So you can't square both sides when you have negatives. You got to get rid of the negative first. The squaring both sides to preserve inequality only works if you've got positives. So we're going to, before we square both sides, which we can do, it's legitimate, but first we have to multiply by -1 and make everything positive. And so when we do that, whenever we multiply an inequality by a negative, we have to swap the symbol. Now we can square both sides. So we'd have k squared less than or equal to k. Now, this is a little fishy, but let's keep going. If we put everything on one side, we just want to know whether that's true or not. We could factor if we wanted. So is that true? So we're imagining k getting very big. Is that true or false? Definitely false. Definitely false. Because if k is getting really, really big, that's positive. Right? So this is false. So inconclusive. Everyone agree with that? So how about this? So one thing we could do is go to the limit comparison, for sure, option. I want to try a slightly different approach there. I want to point something out. So our big issue here was that one thing that we've seen when we do this is that our b sub k often has a piece that's going to cancel when we do this subtraction, but we didn't get canceling here. So what if we did this? What if we said, okay, this divergence series was inconclusive. What about if we stuck with this one? If we factor out the 1/2 and we have this, does this series converge or diverge? Still diverges, right? The harmonic diverges, and if you multiply a diverging series by a constant, we still have diverging. So this still, our conclusion is still diverging because that's still harmonic. But notice the change here. So this is just one thing that we can do. If your b sub k doesn't work, you could massage your b sub k to a different b sub k, and that one might work. Or you could go to the limit comparison, of course. So here, let's just do this, go through the same argument. So we have this 2k minus root k in the denominator. We want to show that it's bigger than 1 over k, 1 over 2k. Our new series is 1 over 2k. And let's just notice this difference here. So here, when we do our cross multiplication, now the 2k's just cancel. Right? We can subtract 2k from both sides, and the 2k from our a sub k, now that our b sub k also has a 2k, cancel, and we have this. And dealing with minus signs stinks, so let's get rid of the minus. If we multiply both sides by -1, oh, we better reverse the inequality. So we have that. And is that true or false? True. K is a positive number. K is going bigger and bigger and bigger. The square root of a positive number is still positive. So this is true. So we can make our conclusion that the original series a sub k, does it converge or diverge? Diverges by direct comparison. Yes. So because that's true, so here's an example where we didn't have to go to the limit comparison test. We just made a different b sub k. B sub k is something you choose. B sub k is a series that you build. And you build it in a way with some guidelines, get rid of stuff that's insignificant. But either one of these is fine. This one converges, same argument, still a harmonic series multiplied by a constant, so it still diverges. But it gives us what we need here so that when we do that subtraction, we get rid of the two, we get a 0 on the left side. Whereas this became very messy, and we never were able to get the right conclusion. All right, let's go ahead and take our break. Take 10. Take 10. And let me pause this. Okay, so far so good. Gosh. So let's take a look at this kind of ominous looking one. Here we have two factors and not two terms. So there's a factor and there's a factor. The b sub k, what do you think would be a good choice to try first? K squared in the bottom? Because k squared goes to infinity faster than natural log goes to infinity, so it sort of dominates. So let's go ahead and do that. So let's choose as our b sub k 1 over k squared. And this is going to be a p-value of 2, which is greater than 1, which is convergence. So that's going to be our comparison series. So we suspect that our a sub k series is going to do the same thing. And that's super plausible, especially here, because when we multiply this ln k, does that increase the fraction value or decrease the fraction value compared to this one? So this denominator is bigger, so the fractions will be smaller. So if we take this k squared thing down here and we multiply it by something bigger than 1, natural log of k is bigger than 1, then this fraction has a bigger denominator, so it has a smaller fraction value. So it should work totally fine. We should be able to use that, and it should work fine. Close that. They're a little loud. Wow. Okay, so let's just go through the math and see that we can do that. So we take our a sub k, we want to show that a sub k is smaller than b sub k. Smaller than converging converges. So 1 over k squared ln of k, is it? Question. Is that true? We can cancel out the k squareds right away. If we multiply both sides by k squared, those are going to go away. And we would have this inequality. And is that true?
Yes.
And the answer is yeah. And now, this series starts at 2, and so 2 is the first k we plug in. Even if that wasn't true for a couple of k's, we would still conclude that it's eventually true because k is going towards infinity. So even if, this was not true for every single k, if it was true for all the k's beyond a certain point, then it would still be okay to say that that inequality is true. We would just say 4k greater than whatever. So this is true. So our conclusion is convergence, yeah. So we converge by a direct comparison test. So comparison tests, a little bit of thinking. I want to go back for a moment to the, let's see, do I want to go there? Do I want to go there? I want to go back up here because I want to mention one thing. Where is it? It's here. Okay. So the primary part of the limit comparison is this thing right here. That's the primary. And that's what we've used both several times now. I just want to talk about these two things for a minute. I won't test you on these two alternate pieces, but I want to at least talk about the logic. All right. So let's look up here at this limit. It says this limit is 0. Okay, so if L is 0, and the denominator converges, so the b sub k, that's always the series we build. That series, so we have that this series down here converges, then a sub k converges. So let's think about this for a minute. So the overall limit is 0. The denominator is going to 0 because the b sub k series converges. If the b sub k series converges, then definitely the b sub k's have to go to 0. Right? A series can only converge if the terms go to 0. So we have an overall limit of 0, and the denominator is going to 0. If the overall limit is 0, that means that that numerator must be going to 0 even faster than the denominator. If the overall limit is 0 and the denominator is going to 0, the only way the overall limit could be 0 is if that numerator is also going to 0, and it's going to 0 at a faster pace than the denominator, so you don't have indeterminate forms. Okay? So if the a sub k's are going to 0 faster than the b sub k's, and the b sub k's converge, then the a sub k's have to converge also, because they're going to 0 faster. Okay. Now, let's suppose that the limit is infinity, and we have b sub k's that diverge. So if the b sub k's diverge, and this limit is infinity, then the a sub k's have to go, we have a couple of cases there. So the b sub k's are either going to 0 slower, the b sub k's are going to 0 and the a sub k's are going to infinity really fast. So it offsets the b sub k's going to 0. Or they could both be going to 0, but the numerator is just going to 0 way slower than the denominator is going to 0. So it's possible that the denominator goes to 0, they both go to 0 at different paces. That's possible. But in either case, if the denominator, if the b sub k's diverge, the a sub k's are just worse. They're worse than the b sub k's because we're getting a limit of infinity. So whether it's that the a sub k's are going to infinity faster than the b sub k's are going to 0, or whether it's the a sub k's are going to 0 way slower, the a sub k's are going to 0 way slower than the b sub k's are going to 0, then you can have divergence. So we're not going to see these two. These two are a little bit taxing on the brain. We're going to stick with this one on the exams for sure. But that's the logic in those two. Top one's a little easier to conceptualize. Okay, let's do pick your own test type of problem. Okay. So choose your test. When you see this series, what do you see? Like the only way we can use our tests is if we have things in summation notation. So we have to, do we see, is it a geometric series or is there a pattern that we could use to create a summation for it? Like from the first question, is it geometric? No way, right? Because geometric means there's a constant multiplier. And if we look here, the multiplication to get over here would be to multiply by, I don't even know what, right off the top of my head. But it's definitely not the same thing that would take us to 3/4. So it's definitely not geometric. That's the one that sometimes we see just showing up in an expanded form. Okay, so we don't, it's not an obvious geometric series, so we can't identify an R. But can we write this in summation notation? Is this one easy enough to write in summation notation? Let's suppose K starts at, feels like maybe starting at 2 is a good thing. And so go up to infinity. What do you think we should put in here? So K is 2. And it's going to be creeping up one at a time. So this is just a K down there. The exponent matches the denominator. And then how do we build the numerator from the denominators? K minus 1. So there we go. So we have that series. So now it's in a summation form where we can look at the A sub K and we can do some analysis on it. Now, what do we notice about this A sub K? Well, let's simplify it first. So let's write it as 1 minus, let's divide the denominator into the numerator. Does that A sub K have a limit of 0?
No.
What is the limit of that?
Infinity.
No.
Sorry, 1.
Not 1.
1 to the infinity.
That's the indeterminate form that it is.
Oh, E.
E to the,
K. No.
no.
X. No.
So the limit has to be a number. The limit's not going to have a K in it. But we're taking the limit as K goes to
no,
infinity.
E to 1.
E to the,
1.
nope,
Infinity.
nope.
Oh.
So we've done this one a few times. Limit as K goes to infinity. This is 1. I could make this a plus if I wanted. Plus in the middle. So we did it in general, where this we called capital A, and then the coefficient up here we called capital B.
So negative.
So this is going to be e to the negative 1. So that's capital A, and the one that we did it in general, so we had e to the AB. This converges to e to the AB, so we multiply the negative 1 and the positive 1 and get negative 1. This is not equal to 0, so what's our conclusion? If the limit of a sub k is not 0,
Does not converge.
it diverges by the divergence test. Right? The only way a series can converge is if the limit of a sub k is 0. So if the limit of a sub k is 0, then we say the divergence test is inconclusive. The divergence test can only detect divergence. So your conclusion is, oh, it diverges because the limit's not 0, and if the limit is 0, the test is inconclusive and you go to some other test. So this is not 0, so therefore diverge by the divergence test. Okay. So on the exam, if the question says find the limit of this using the log limit process, then you've got to go through the long process, take the log of both sides, take the limit of both sides, use L'Hopital's rule, etc. If it doesn't say that, you can use the shortcut. So if it's not a problem that's testing you on proving that the limit is e to the negative 1, you can use the shortcut. But if the question says use the log limit process, then you would have to go through that whole process that we've gone through a few times. Okay, let's look at that one. So this one is interesting. What's your suspicion? Converge or diverge? Diverge. Everyone agree? Diverge? Let's think about what we know. We know that if it's just 1 over k, this diverges, right? This is harmonic, which means divergence. Doesn't this denominator grow even slower than this denominator? So these fraction values are going to 0, but they're going to 0 even slower. So these go to 0 pretty slow. These go to 0 even slower because natural log is going to infinity slower than k is going to infinity. So our suspicion is that that thing's got to diverge. And this is a little funny. We are going to create, this is going to be our b sub k. We are going to use a comparison test here. But it's not that we're building the b sub k by taking away something that's insignificant. We're just going to compare it to sort of the series that most closely resembles what we see. So let's see. So b sub k series diverges because it's harmonic. So if we want to use that information to do something with this series, do we want to show that the a sub k's are bigger or smaller than the b sub k's? Bigger. Bigger than diverging will diverge. So we want to show that the a sub k's are bigger. And so the a sub k, we have this. We don't know, so we want to show that. Cross multiply, and we want to show that k is bigger than natural log of k. Well, if we look at a graph, we know that the log function looks like this. That's there at 1. And we know that the identity function, y equals x, looks like that. So is that true?
Yes.
Yeah, that's going to be true. That's going to be true. And it's not... so that's going to give us divergence. So that's not mathematical proof that k is bigger than natural log of k, but we've graphed them enough that we just sort of know that as a basic fact, that k is bigger than natural log of k. There are some calculus techniques that you can use to show it. Like you can form the function x minus ln x and take its derivative and show that that derivative is always positive, so they're getting further and further apart. You know, so you can use kind of an argument that's like induction, where we can plug in 1, and so if you plugged in 1, what's natural log of 1? 0. So we have 1 bigger than 0. Yeah, that's true. And then you think about going out to 2. Natural log of 2 is less than 2. Natural log of 2 is 1 point something. It's less than 2. And you could build a function that's x minus ln x and just show that that difference is growing. You know, we know that they're definitely satisfy the inequality here. Green is bigger than red there. And then you can build the function that measures green minus red and show that that keeps getting bigger. So they cannot... they have to satisfy that inequality if the difference is getting bigger, you know, all the way out to infinity. Okay, so that's true. So we know that fact. X is bigger than ln x. So comparison test here, we used a direct comparison. So this was by direct comparison. The big difference here is that we didn't just chop off a term. We actually created a whole new function, but we created a function that was most closely resembling the one that was given to us. A couple more. What test do you think for 51?
P-series, right?
So P-series is piece of the puzzle, but what would the test be? Because it's not a P-series immediately. So what are we going to do to, what test would we use? Comparison test.
Right.
So we're going to build a B sub k. So if we're going to build a B sub k, that's comparison land. So the first thing we're going to do is ditch the 3. And then we would simplify, and we would get 1 over k cubed. So P is 3. So is that converge or diverge?
Converge.
That's bigger than 1, so it's a converge. So 3 is greater than 1, which tells us converge. So our B sub k series converges. So we would want to show that the A sub k's are smaller than the B sub k's. So smaller than converging converges. So A sub k, just going to sort of fill in the A sub k and the B sub k. Put a question mark because we don't know. Put our B sub k over there. And before we finish the math of that, we should know already whether it's going to work or not work. Is it going to work?
Yep.
Because when we look at our B sub k, we can look at this form of the B sub k. This denominator is increasing from that denominator, so the denominator is going up, which means the fractions are going down. So these fractions are smaller than those fractions. So we will be able to get to the right conclusion. So we get k to the 11, cross multiply. K to the 11 plus 3. And let's go down to the constants. It's nice to go down to the constants. That right there is true, which tells us that we have convergence by direct comparison test. Okay. So this series is not P series, but it's P series-ish, which means we're going to use a direct comparison. All right, how about this thing? First off, do you think converge or diverge?
Converge.
Converge. If we look at that numerator, the numerator is a wobble, right? It's between negative pi over 2 and pi over 2. Right? Everyone agree? Inverse tan is bounded. And what we've seen is that when we take a limit of a bounded, when we take the limit when we have a bounded function over something going to infinity, that bounded function acts very similar to a constant. And so our suspicion should be here that the denominator is growing so fast and the numerator is acting kind of like a constant. It's never any bigger than pi over 2, that k squared is going to dominate and that this thing is going to converge. And we should be able to compare this to that function that you all kind of suggested, this one. You know, if we look at the numerator kind of like a constant, then let's compare. And we have here that p is 2, which is greater than 1, which tells us convergence. So will direct comparison work here? Will we be able to show, so just think in your mind, can we show that the A sub k's are less than the B sub k's here? We're not going to be able to show that, right? Because this numerator is bigger. Everyone agree? Right, that numerator is bigger than this numerator, so this one's actually bigger than that one. So here we have that dilemma that we've done in 2 different ways. One way we jumped to the limit comparison test, and the other way was, hey, can we modify the B sub k to make the inequality work? Could we do that? Can we modify this big B sub k so that the inequality will be favorable to us? if this is always less than pi over 2, couldn't we pick a numerator here that's a constant that's bigger than pi over 2? Like if we, what's a number that's bigger than pi over 2? So pi, how about, let's go with an integer.
No. 4.
So yeah, so the biggest this is pi over 2, so that's kind of like 3.14 over 2, so about 3/2. So 2 would be bigger than pi over 2. 4 would also work, whatever. We could pick pi too. Pi, it doesn't really matter, but picking an integer is just a little bit simpler. So if we did pick an integer, if we change that to a 2, does that change the convergence of this series? No, right? If we take a number 2 and multiply it by a convergent p series, the series still converges. Right? We still, this is 2 times a convergent p series, so still have convergence. But then notice what happens. Then here, when we do arctangent of k divided by k squared, is that less than or equal to this? Now we have arctan of k less than or equal to 2. And we see, oh yeah, we could pick any constant that's greater than pi over 2, and the inequality will pan out in our favor. This will be true, which will be convergence by DCT. Now, if we didn't want to fiddle, if it wasn't easy to fiddle with b sub k, then we definitely want to go to limit comparison test, and that will work out fine in this case too. But just so, you know, those are the two options. If your inequality doesn't work, you could fiddle with b sub k or go to the limit comparison. Either one's going to work. So that's the comparison test and the two comparison tests. Now, let's go to another special series. So our special series so far, we've had a geometric series, we've had a telescoping series. The alternating series is kind of special like that. It's going to have kind of its own rules. Now, the first alternating series that we're going to look at is the alternating harmonic series. So there's a picture of the expanded form of the alternating series. The alternating series, this alternating harmonic, is going to converge. So we know that the harmonic, where everything is positive, diverges. So the alternating harmonic, all we've done is turned every other term negative. So we can think of the positive terms as adding and creating a sum that's, you know, increasing, but then we're subtracting off little pieces along the way. And this is going to create enough subtraction that the overall limit will exist. And it's going to turn out that this alternating harmonic converges to the natural log of 2. We're not going to show why that is, but that you can show that that is true. So the harmonic we know diverges. P is 1, which is not greater than 1. Here is a picture of the alternating harmonic. So the alternating harmonic at 1, we're up here at 1, and then we subtract off 1/2, and then we add a third, then we subtract a fourth. So first off, let's just look at what's happening. So this is an alternating series that's going to converge. It's like a horizontal asymptote. And just notice that we subtract a half. That means we're going through the eventual limit. And then we add a third, and we pass back through the eventual limit. Then we subtract a fourth, passing through that limit. Add a fifth, subtract, blah, 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 all the way down. So just keep that process in mind, that we're going through the limit as we do our adding and subtracting. When we add, we're going up through the eventual limit. When we subtract, we're going down through that eventual limit. The sequence of partial sums looks like that. There is no pattern that you will be able to find So with our geometric series, with our telescoping series, we found in S sub n that we could then take the limit of. Here, there's going to be no way for us to find this. We are not going to be able to find that. That is not happening. We can't find it. So we can't just take the limit of S sub n to see if it converges or not. Okay. But when we look up here, we've got very strong visual evidence that it converges. And there's some very smart people that eventually figured out that it converges to natural log of 2, which is super interesting. So how do we show, if we have this special series called an alternating series, how do we show it converges? This is going to be one of the simplest tests out there, the alternating series test. Here is the alternating series test. Now, first off, in my opinion, they have these backwards. Let's look at number 2 first. That's the divergence test. If you look at the limit of a sub k, it has to be 0. We already know if the limit of a sub k is not 0, we have divergence. If the limit of a sub k is 0.01, that means we're essentially adding 0.01 to 0.01 to 0.01, and that's going to diverge. If you add any given number to itself forever, you have divergence. So this is something we should always consider anyway. So that really makes the most sense to be first. Because we should at least think about the divergence test, whether we formally write it down or not. So I always do that one first. Now, one thing I need to point out to you that's important is that a sub k does not include the minus. When we are looking at an alternating series, for an alternating series, this a sub k is not including the minus. So this is a sub 1, this is a sub 2. We don't include the signs when we talk about a sub k for an alternating series. So this a sub k, right, it's separate from the minus. So a sub k is positive, and then we multiply it by a negative to create the negative terms. So we want to keep that in mind. And here is the important crux of the alternating series test. So we have our inconclusive divergence test. The limit is 0, so it might converge. All we have to do is show that the terms are getting smaller. So we've got, sometimes some books will do this in one step instead of 2. So we have a limit of 0, and a sub k plus 1 is smaller than a sub k. That's what we need to show. So if the limit is 0, we're imagining ski slope, it's going down to 0, and each magnitude as we go further and further is smaller than the prior magnitude. A sub k plus 1 is smaller than a sub k. Now, the a sub k's are all positive. The minus is not part of the a sub k's. So when we go look at this prior picture again, so let's get this, let's get to right, can I get both of them in there? Let's look here. So here, again, the minuses are not part of the a sub k. So if we can show, here's a sub 2. A sub 2 is smaller than a sub 1. A sub 3 is smaller than a sub 2. A sub 4 is smaller than a sub 3. So we're just looking at the absolute values, the magnitudes. So all we have to show is that we have this setup where the subsequent term is smaller than the prior term. If that's true, and the limit is 0, that's it. Then we have convergence by the alternating series test. So the alternating series test just says that our sequence of magnitudes is decreasing to 0. That's how you say the alternating series test in one sentence. The sequence of magnitudes is decreasing to 0. That is the alternating series test. So the sequence of magnitudes going to 0. That is the alternating series test in one sentence. The sequence of magnitudes is going to 0. All right. So here's an alternating series right there. If you see that the series is alternating, guess what test you use? The alternating series test. So that's a nice thing, because a lot of the series you look at and you're like, I don't know what test to use. P-series, integral test, we have a lot of tests. So alternating series test. So let's do this one. First step. The limit of a sub k as k goes to infinity. So I'm going to do it in this order, the divergence test, if you will. And remember that a sub k does not include the switch. The switch is the minus 1 to the k. We ignore that. A sub k is not including the minus sign. What is this limit? As k goes to infinity. 0. Check. Alternating series has two things we have to check. It's more of a verification than anything else. 2, we want to show that a sub k plus 1 is smaller than or equal to a sub k. For our purposes, it's smaller. It's going to be decreasing. We don't have the non-increasing things where we have horizontal stuff happening. The terms are going to be they're either going to be decreasing or not decreasing. If they're decreasing, we already know they go to 0. So now if we can show that they're decreasing to 0, we're good to go. That there's no weird oscillation or something. Okay, so a sub k is 1 over the square root of k. And I always write it this way, like a sub k on the left of a sub k plus 1, because I'm thinking the way we read. We are reading left to right. When we envision the tail of our sequence or series, we're going out to the right. So they wrote it this direction, which I find awkward. We already know that the a sub k's are positive. I would rather think of a sub k here in the next term to its right. Like that visually matches what it looks like when we expand it. So I will always put it with the a sub k to the right of the a sub k. So we're shrinking as we go to the right. So a sub k plus 1, we just plug in k plus 1 for the k. We want to show that. Crisscross, cross multiply. Once everything's positive, you can square both sides. There's no negatives here to worry about. If everything's positive, you can preserve equality. You can preserve the inequality with squaring. Subtract the k. Get down to a numeric inequality that we can solve by inspection. That is true. So we have check and check. Done. So therefore, converge by AST. So if both those things check out, that's it. We've now proven, feels kind of way too easy, that that's all we have to do is show that the limit is 0 and that the terms are decreasing. So that's it. That's all we have to do. Very nice. And the fact that it's very obvious when you have an alternating series because there's a switch. So it's really easy to know when, well, maybe I shouldn't say always. If you see the switch, you know it's alternating. This is a disguised switch, but usually, like you look down here and you see, -1 to the k, it's alternating series, then we're going to use the AST. Now this first one, notice that that really is just a hidden switch. Right? When k is 1, what's cosine of pi?
-1.
-1. When k is 2, we have cosine of 2 pi, which is +1. So it is just going to go from negative to positive. So this one, the first term is negative here, though. The last one we had, the first term was positive, and the next term was negative. So we have that. But that is just a switch. If you wanted to, you could actually change this. If we wanted to, we could rewrite this. K equals 1 to infinity. We could make this negative 1 to the k or to the k plus 1. Nope. Okay. So remember the first term up here is negative. If you plug in k equals 1 here, you get cosine of pi. Cosine of pi is negative 1, so we want to start with a negative. And because this index is odd to begin with, negative 1 to the 1 is going to be negative 1. So that's going to give us a starting value that's negative. And if k is 2, then we get to positive. So when k goes to 2, negative 1 squared is positive 1. So we could do this. These are equivalent. But we don't have to. The two parts of the AST say, what is the limit of a sub k as k goes to infinity? So we would take the limit of, let's just leave it as the original just because that's what we were given. So what is that limit? 0. Now, what is the math? You don't have to do this. We don't have to show. We've talked about it, though. What is the mathematical way that we would prove that that limit is 0? We had a technique. If the numerator was wobbling, what did we do? Squeeze theorem. That's exactly right. The squeeze theorem is what the mathematical justification would be. We can envision cosine is always between negative 1 and positive 1. And then if we divide everything by k squared, we have a negative 1 over k squared on one side, a positive 1 over k squared on the other. The limit of both of those is 0. So the limit of the thing in the middle is also 0. So the justification would be squeeze theorem. Now, you don't have to show that here, but just so that it's kind of in your mind. So that would be, not squeegee. Squeeze theorem. That is a U. So that would be the justification. Okay, but that first part checks out over here that, the divergence test is inconclusive. Right, so this, whenever the limit of a sub k is 0, we might have convergence, we might have divergence. So just in parentheses, I'll just say that dt inconclusive. Okay, second part, we want to show that the terms are decreasing. We now know that the limit of them is 0. If we can show that they are decreasing to 0, there's no weird business going on, then we're done. So we would like to show, we want to show that as we go further out, the terms are getting smaller. So we write down our a sub k. Or k squared. Now here's where we might say to ourselves, eek, let's convert this over to that form. So pi times k plus 1, all divided by k squared. Okay, so, I did something very dumb. Does a sub k include the minuses or not? No. We don't need the minuses, right? A sub k does not include the minuses. So all we have to do is this. Oops. The a sub k, because it's not a minus 1 to the k looking thing, I just sort of wrote it in there. But remember, a sub k does not include the minus, so it's really just the 1 over k squared. And so for a sub k plus 1, we just replace the k with k plus 1. Disaster narrowly averted. All right, so let's see. Cross multiply. And as I cross multiply, I am going to expand the k plus 1 squared. Subtract off the k squareds. And is that thing true? 2k plus 1, is it positive?
Yes.
K is a positive number.
Yep.
2k plus 1's got to be positive then if k is a positive number. So that is going to be true. So now we have 2 checks, that and that. So therefore we converge by AST. So 2 steps. Show the limit of a sub k is 0 and show that the terms decrease. Let's take a look at this one. So, step 1, let's take the limit of a sub k, as k goes to infinity. And again, remember, we do not include the switch for a sub k. So we have the limit of 1 divided by k ln squared of k. Well, k goes to infinity, ln k goes to infinity, ln k quantity squared goes to infinity. So the numerator is constant, the denominator is going to infinity, so the fractions go to 0. So that checks out instantly. So the second step, we want to show that it's decreasing. The terms are decreasing. So we want to show that a sub k is greater than a sub k plus 1. A sub k is everything in the summand except the switch. So that's what we want to show. All right, now this one is going to be a little, it's going to be a little complicated. It's a little complicated because ln of k and ln of k plus 1, there's no way to simplify that quotient. You know, there's no cancellation. So here's what we're going to do. This one we're going to approach a slightly different way. Most of them we can get the inequality where we have a 0 on one side and we can kind of look at the other side and it's obvious. Here's what we're going to do. We're going to group things in the following way. We are going to group the k and the k plus 1 on one side. So I'm going to multiply the k plus 1 over there. And then I'm going to put the log thing over here. So this is going to be log of k over log of k plus 1, and all that is squared. So the log of k squared comes over here. We just pull the square out. Tell me this. Is this quantity less than 1, or is that quantity greater than 1? Less than 1? Natural log of k plus 1, if we look at the natural log function, when we're visualizing the natural log function, it's doing this, right? So k plus 1 is further to the right than k, so natural log of k plus 1 is going to be higher than natural log of k. So this one over here, that is always going to be less than 0. Less than 1. So some sort of fractional value. What about the left-hand side? That is always greater than 1. This is always greater than 1. So for every k, the right side is less than 1, the left side is greater than 1, so is the inequality true or false? True. If this side's always bigger than 1 and this side, bless you, is always less than 1, the inequality is true. This is bigger than 1, that's less than 1. A number that's bigger than 1 is always bigger than a number that's less than 1. So this is in fact true. So therefore, we have converge by alternating series test. A little bit sneaky. Let's try one more here. All right, so we see some shenanigans in there. We have a factorial. We have a power tower. Hopefully they don't cause us any grief. First step, we want to take the limit of a sub k as k goes to infinity. A sub k is everything except the switch. So we've got that. So this is in fact indeterminate. Right? This is an infinity over infinity situation. We would love to be able to use L'Hopital's rule, but we can't use L'Hopital's rule because we don't know how to differentiate factorials and power towers. So we just have to refer to growth rates. Which one of them grows faster, power tower or factorial? Power tower grows way faster than a factorial, so this limit is going to be 0 because the dominant term is in the denominator. Denominator is going to go to infinity faster than the numerator. So that checks out. And then our second step, we want to show that the terms are decreasing. So we want to show that as we go further out, the terms are getting smaller. So let's see. So we have a k factorial over k to the k. We want to show that that's greater than k plus 1 factorial over k plus 1 raised to the k plus 1. So that's what we need to show. So let's combine a couple of steps here. Let's cross multiply. No, I'm not going to cross multiply. I want the factorials on the left, and I want the power towers on the right. So I want to group factorials together and group power towers together. So I'm going to divide both sides by k plus 1 factorial. And as I do that, I'm going to rewrite k plus 1 factorial as k plus 1 times k factorial. Everyone remember that? Like if you have 6 factorial, you could write that as 5, you could write that as 6 times 5 factorial. Or you could write that as 6 times 5 times 4 factorial. Right? You can drop the factorial sign into whatever position you need to make it convenient. So k plus 1 factorial means k plus 1 times k minus 1 all the way down to 1. So it's k plus 1 times k factorial. All right. And I'm moving this power tower from the bottom left up to the top right. So I'm multiplying both sides by k to the k. And what I'm going to do with this denominator here, can't I rewrite this as k plus 1 times k plus 1 to the k? k plus 1 to the k plus 1. You can break it apart into two pieces with the laws of exponents. And doing that is strategic because now this k plus 1 on both sides, this will cancel. Multiplying both sides by k plus 1, that'll be gone. The left-hand side, we also have this k factorial over k factorial. That will cancel. So the whole left-hand side ends up being a 1. So question mark. And over here we end up with k over k plus 1 raised to the k. Is that true? So in here, what do you think? Is that true?
Yes.
So in here, this piece right here is always less than 1. So if you take a number that's less than 1 and you start multiplying it by itself, it's going to get smaller. It's going to go closer to 0. So in other words, no matter what the k value is, this base is always less than 1. That exponent is going to create something that's less than 1. Do we agree? So for any particular k. Now, what if we were asked, what is the limit of k over k plus 1 to the k? So just out of curiosity, because this kind of combines a couple of ideas. So you may say, oh yeah, for any particular k, that's true. So it's true for all k, but what is the limit of that thing?
0.
Limit of that is not 0, or it's not necessarily 0, I should say.
It's a...
Because it's a 1 to the infinity thing.
This can be... Right.
So here's the trick. We can't split this fraction, but what we could do is flip it. If we flip that fraction, then we toggle the exponent to be a negative, because -1 exponent flips. Then we split the fraction. And so that's going to be e to the -1 again. So we take the -1 as the b and the positive 1 as the a, and it's e to the ab. So it's 1/eth, and that is less than 1, 1 over e. So this is true for all k, and so it's just an interesting question. Well, if it's true for all k, what does happen as you go further and further out in the tail? These terms aren't quite going to 0. For any particular k, it's a fraction, but the smallest the fraction will ever be is 1 over e, or about 1 over e. It's not going to actually get to it. But regardless, the right-hand side is always less than 1, no matter what. So this is true. So that checks out. So therefore, we have convergence via the AST. All right. Ready for a weekend? Got to catch up now. It's like between Tuesday and Thursday, so short. It's like it really should be like Monday and Thursday would be, kind of ideal. Or Tuesday and Friday. All right, well, we'll stop there. Anyone that wants to stay and do more math, you're welcome to. You can always do more math.